Design of concrete structures, Chapter 4, Flexural Analysis and Design of Beams. Uh, Stage of stresses and strength analysis in flexural analysis. So according to ACI code 19.2.4, the formula for modulus of rupture for concrete is Fr, and that's equal to 7.5 times lambda times the square root of F prime C. Uh, concrete specific strength F prime C. So let's see what's lambda in this equation for modulus of rupture, which we'll talk about it later on. And the formula is 7.5 times lambda times square root of F prime C, which lambda in the equation goes by three categories. And the first one is normal weight concrete, that in that case lambda is equal to 1. Sand lightweight concrete lambda is 0.85. You can see easily the reduction pattern of lambda, and also all lightweight concrete, which lambda is 0.75, and it just replaced in the modulus rupture to calculate Fr. And what is the modulus of rupture itself? For many years, tensile strength has been measured in terms of modulus of rupture, which is F sub R, which is the computed flexural tensile stress at which a test beam of a plain concrete goes failure or fractures. And again, based off a ACI code, Fr is 77.5, the square root of F prime C, if lambda is equal to 1, and lambda is mainly placed around 0.75 to 1, and that for a compressive strength above 2000 psi for normal weight concretes. Let's see how concrete structures behave in different stage of stress and stresses and strength in flexural analysis. So we do have three stages. The first one is stresses in elastic domain, and when the section is uncracked. The second one, the stresses remains in elastic domain, but the cross section goes by some kind of tensile cracks begin to appear, and the final one is flexural strength, which is ultimate load design or ultimate stress design. The first one is when a stress FCTF stands for stress of concrete in tensile section is smaller than F sub R, which is a modulus of fracture. And the second one is then FCC, stress in concrete in compressive part, this time is smaller than 0.5 times, this time F prime C, which is a specific strength of concrete. And then the last one, ultimate load design, is then FCC, stress in concrete in compressive part of the section is higher than 0.5 times F prime C. So the first one, which the stress is in an elastic domain and section is uncracked, is then again FCT is less than a modulus of rupture, and that's when the section transform, the tensile steel rebars transform to an equivalent area of concrete, but the whole area remains uncracked. So the cross section is intact. There is no rupture in cross section. In the second case, stress elastic and section crack is when FCC or stress in concrete in compressive part is less than half of prime C, and that's when the cross-section rupture or divided into two parts. This is the neutral line remains at the interface of division, and that's the below part is a steel uh, concrete which is equivalent concrete of steel, and the top part is the concrete part. But you can easily see the first section divided into two sections. That was, we call it the cracked section. Mhm. And the final one, which is flexural strength in ultimate load or ultimate stress design, is then FCC stress in compressive concrete yet exceeded the half of F prime C. The visual shape of the cross section remains the same with section 2. The difference is FCC is this time higher than half of F prime C, and yet the nuance difference, the height of Y bar from the top of the section yet reduces uh, higher degree. That we will talk about it in next videos. Thank you. We will put it into problems in next video, and thank you.